Hello, everyone. Welcome to the Nomads Podcast. I'm your co host Prachi.
And I'm your co host Bhavya.
In the 1920s, physicists like Schrödinger, Heisenberg, Einstein, Planck, and many others realized something deeply unsettling and beautiful. The universe at microscopic scales is nothing like what we observe in everyday life. This was the era when quantum mechanics was discovered. And I'm intentionally saying discovered, not born, because that choice of word matters. Quantum mechanics isn't just a framework we invented. It's closer to the idea that we uncovered something that was deeply true about reality. What makes this discovery so fascinating is that quantum mechanics feels so far away from how we perceive the world, and yet it is literally what the world is. The universe is fundamentally governed by quantum laws, and what we experience in daily life, objects with definite properties, predictable motion, a world that feels stable and classical, can be thought of as an emergent phenomenon. And the way we're taught physics reflects that. When we start learning physics in high school, we begin with the rules of the world we directly experience. Classical physics. Only later do we upgrade to quantum mechanics and we try to map our classical intuition onto this quantum world. And we do that for a very human reason. From birth, our intuition has been trained on the classical world. So when quantum mechanics tells us something that doesn't match that intuition, it feels non-intuitive. But what if we flip the script? If the universe is fundamentally quantum, why don't we start there? Why don't we build our intuition from the quantum picture first and then understand classical reality as something that emerges in the right circumstances? That question, this idea of taking a quantum first approach, is exactly what our guest today, Ashmeet Singh, is thinking about. Ashmeet is a theoretical physicist who completed his PhD at Caltech and is now a professor of physics at the Indian Institute of Technology in Delhi. Along with being a brilliant physicist, Ashmeet is also an avid science communicator, someone who has a real gift for explaining complex ideas in physics in a way that's clear, intuitive, and genuinely exciting. In this episode, we also talked to Ashmeet about his personal journey through academia, how he navigated his path from IIT to Caltech to IIT, what that transition felt like, and what he learned along the way about doing research and finding a place in physics. We're genuinely grateful to IIT Delhi for hosting us, for both giving us this beautiful space to sit in and record, and for inviting us to give colloquium talks while we were in India. And a special thanks to Sarthak Parekh for being a wonderful host and organizing everything so smoothly. So if you've ever wondered what it would mean to understand the universe starting from quantum mechanics, treating classical reality not as the default, but as the thing that has to be explained, then you are in for a treat. So let's go.
Ashmeet Singh, welcome to the Nomads Podcast.
Well, thank you. Happy to be here. Yeah.
So, as we've searched you on the internet and read about your profile, I've noticed that you have quite a substantial range of interests, and we hope to sort of talk about some of them as we progress in the podcast. But a central theme of your work has been what you call a quantum-first approach to space, time, gravity, and cosmology. So let's start with that.
Sure.
What do you mean by quantum first? And how is it different from other approaches? How are they not quantum first?
Right. So that's a lot to unpack there, in terms of quantum first, and you're having an approach towards so many different things, including space and time and gravity, cosmology, words which as physicists or even scientists, we think are fundamental to how we understand the world around us, right? So let me kind of take you back a little bit as to how we typically do physics. We all do physics here and we love doing it. And traditionally, because we as human beings are classical organisms, right? We are massive, we are giant, we live in this mesoscopic world, not too big, not too small.
Right.
We're not microscopic, we're not cosmological, somewhere in the middle.
Right.
And we evolved to kind of live in this range. And in this particular range, the kind of laws that very well govern what we understand are these classical laws of, let's say, Newton, for example, right? How things fly around, laws of motion, thermodynamics, electromagnetism. All these things are classical laws, so to speak. And by classical here, I mean that there is a certain understanding of what kind of variables are actually definitive and what kind of variables make sense. So, for example, if I want to describe this nice particle here, I would say, if I can tell you what the particle's position is and the particle's momentum is, I know everything about the particle. There's to be known, right? And then if I can tell you further what it's going to do, how its position is going to change in time, how its momentum is going to change in time, I can know what's going to happen next with the particle, for example. So a classical theory, in that sense, tells you, predetermined, what kind of variables you must talk about. And from there, everything in the world around you makes sense. Now, that's all nice and good. But what we know is that at the microscopic scales, the laws are a little bit different. Quantum mechanics comes into play over there. Now, traditionally, as scientists, as physicists, we have tried to unify different forces. So we want to basically get a quantum understanding of, for example, the electromagnetic field, for instance. We want to understand a quantum approach to the strong nuclear force, for example. So traditionally, what we have done to do this over the last almost, I want to say, 100 years now, is that we start with a classical theory, right? So what you and I understand as space around us, as time around us, we understand, hey, there's a particle here, there's a field over here, something like that. And we start with this classical thing, right? And then we try to impose quantum mechanical rules on this classical thing.
Right.
So Heisenberg gave us an understanding of what it means to be quantum, a certain commutation relation between certain observables, for example, and we try to impose that on these classical observables. The way I mentally picture this is that we are taking a dish, which is classical, and we sprinkle the salt of quantum mechanics on top, and it adds a flavor to it. It changes the flavor, let's say.
And that's what goes by quantization.
That's exactly what I mean by canonical quantization.
Got it.
Canonical here meaning there's a certain rule, there's a certain approach which you don't question too much.
Right.
And that's again important that we don't question it too much. And it's worked beautifully for the last almost 100 years. We don't question it. We take these classical variables, sprinkle our quantum rules, and voila, there's a quantum mechanical theory of something.
Correct.
A quantum theory of n particles, a quantum theory of, let's say, electromagnetic field, the photon, whatever you want. It's worked wonders. And the standard model that we have of particle physics is a glowing representation of this, right? We took classical electromagnetism, we took our understanding of nuclear forces, and we combined them all into one, into this so-called electroweak theory,
Correct.
where we have unified electromagnetism, strong force, weak force, into a quantum theory, as
Right.
far as we understand. So this is what is canonical quantization. We have quantized what was essentially a classical theory.
Right.
Now, one misfit remains amongst the four fundamental forces. So we've taken into account electromagnetism. We have done wonders with strong force at the nuclear scale, weak force or radioactivity. But gravity has been like a sore thumb that's been sticking out and, asking for attention, like, what do you do with this?
Right.
So people, of course, said, hey, it's canonical. You don't ask questions. You just shut up and calculate and you go and do it. So
Right.
people tried, and earnestly they tried, and there was good hope that this should have worked out. But gravity did not really fit into this paradigm where I could start with classical gravity, which for me at least means Einstein's theory of relativity, where gravity itself is how space and time deform and curve as a response to energy and matter. And then we wanted to kind of quantize this.
Right.
Now, people tried a lot. And for reasons both mathematical and conceptual and fundamental, this approach didn't do very well, right? And people had to try different, bells and whistles, and it's still an ongoing kind of an endeavor that people have. But it's not really worked very well. And that might, make some people unhappy that that's what they do. And I respect that completely. But as scientists, I feel we must be a little critical about what we are trying to do, right?
Of course.
So now one thing is, when I think about gravity, Einstein tells me that gravity itself is space and time, for instance. It's the metric, the manifold, and how the geometry on it lives, basically. So typically, when we try to quantize something, we start with this notion of what the classical picture is, right?
Right.
I start with the notion of particles. I start with the notion of space and time also.
Mm-hmm.
I know what the space and time is. Is it a flat space-time? Is it a curved space-time? Is it a Riemannian space-time? Is it Minkowski? Is it Schwarzschild? Whatever it might be.
Correct.
We start with this notion of a background geometry.
Mm.
Right.
And then on this geometry, we try and sprinkle our quantum mechanical rules. Now, that's not worked that well. So the question that we are asking, and by we, I mean this royal we that I'm a part of this group where many people have been trying to approach this in the last a decade or so, I want to say, where we want to flip the tables. Rather than starting with classical space-time and trying to canonically quantize it, we said, how about we start with quantum mechanics, whatever that means in its bare minimum form, and try to gravitize quantum mechanics on the other hand.
Okay.
So can we start with these minimal elements of quantum theory and can we put them together in a certain way which starts to resemble space and time? So space-time emerges from quantum mechanics, and then the hope is if it emerges, it's quantum mechanical right from the start. So that's kind of our approach, kind of flipping the tables, quantum first approach to what we know as space-time and gravity.
I see.
Okay. So in your website, and you've mentioned in like a lot of your work, you say that nature is quantum mechanical from the start, and the classical limit emerges in certain circumstances. So first question is, what are these certain circumstances, and are they unique? Like, can we have different classicality emerging from different circumstances, or is it like unique and that's why we see the world that we do right now?
So honestly, I don't know the answer to that question. But let me kind of go back a second here, where you talked about nature being quantum mechanical at the start. Now that itself is a loaded statement, right? And we believe that to be true, but are we 100% certain? Not really.
Right.
There could be laws of nature which deviate from quantum mechanics. There could be collapse models. There could be stochastic evolution. There could be hidden variables. Any kind of things are possible. But so far, at least our experimental evidence suggests that quantum theory has held up its ground in whatever we have seen so far.
Yeah.
Right.
So kind of going off of that quantum mechanics is what universe seems to prefer as its fundamental structure. Now, what kind of circumstances under which classicality emerges? Now, it's an interesting question because first question is, why do we even need to emerge classicality, right?
Okay.
Now, let me kind of take you back on the classical side for a second. So if I say I have n particles. Now, as physicists, we would say these n particles, this lives in a 6 n-dimensional phase space, right? So 3 n dimensions for the positions, x, y, and z, and 3 n dimensions for the 3 momenta coordinates, p, x, p, y, p, z, for example.
Spot on, yeah.
And you specify a point in the 6 n-dimensional phase space, and the theory is known to you. Evolution is Hamilton's equations. You are done, right? So I could have told you, hey, friends, here I have a theory of a point in a 6 n-dimensional space evolving under a certain, Liouvillean-like evolution. It's an exact theory.
Right.
Why would you want to decompose it into n particles living in physical space and those particles interacting via local interactions? Is there a use to that, right? And is that unique, you might say? So that's your question about the uniqueness. And I don't think it's unique in that sense. The essence of classicality is, at least to me, what I think is useful for us as these classical organisms who live in this not too big, not too small kind of region of the universe, right? So for us, what is useful in terms of how to describe things, how to understand and predict the universe around us, that kind of gave us a preferred way of thinking about what kind of features to look for. So maybe in that sense, we have a target of what we want to describe in the classical terms, which is also a little murky because it depends on what we want to describe in the first place,
Yeah,
right?
exactly.
So in that sense, now coming back to your question about quantum mechanics. Now, quantum mechanics, the way I see it, is a very simple theory. Now, people might say, oh, I've had troubles, doing undergrad and grad quantum, and tunneling really messed me up and whatnot. But at its heart, quantum is a very simple theory. It's, a vector in a large dimensional vector space, a Hilbert space. And that vector just rotates unitarily under Schrödinger's equation. And that's
Basically.
it. Again, I give you the vector, initial condition. It's a first order differential equation. Keep solving it. you know everything there is to know about it.
Correct.
Under what circumstances do you want to describe that large vector as particles living on a space-time? That's again
Right.
where, you know, you and I come in to understand the world that we know lives.
Of
we
course.
live in.
Right.
It's almost like a projection of that
Right.
vector, let's say, that state onto what we sort of observe.
Correct. That's
Correct.
how I think about it. So is
Right.
it unique? Maybe once we decide what classicality really means, maybe it's unique. But of course, we know there are dualities that exist in physics, that a theory can look two different things on different
Yeah.
sides.
Correct.
So it may not be really that unique, but I would expect that once we find this bridge between quantum and classical, even if it's not unique, it's only a few possible solutions, and we can maybe pick out all those solutions. So that's what I would say to that. Yeah.
Interesting.
Right.
So in this whole sort of emergence story, you said, this is going back to something that you said. You said that there's a background, and on top of we define a lot of structure on that background, and then we sort of sprinkle these quantum rules. So when you flip the narrative and you start with quantum mechanics, tell us why there's no background required there. Why you can start with something, something like a vector in a Hilbert space, and then things can emerge from there. How does that happen? Or like, how do you think that happens?
How I would think that
Yeah,
happens.
yeah,
Because
yeah.
again, had we done it, I would probably be in Stockholm right now. But the way I would think that it should happen is, see, quantum theory, as far as we understand it at its basic level, doesn't include words like space and particles and interactions per se in it. Now, of course, when we teach you quantum mechanics, we use those things because otherwise, how
The
do
intuition
we
gets lost,
talk,
yeah.
right? We need to have this common vocabulary of what we can relate with.
Correct.
But again, at its heart, it's all there is this vector in Hilbert space, right? So the question is, how do you start from here, and how do you go to this notion of background coming in? Now, the reason we don't want to have a background is because if you want to get a quantum theory of gravity to me again means space and time. And quantum mechanics allows superpositions of underlying different configurations, classical configurations per se. So if we want to have superpositions over different space-time backgrounds, which a quantum theory of gravity hopefully should admit because it's a quantum theory of space-time.
Right.
And if you start by fixing a background, you kind of already are limiting what you can do with it. You can only do slight perturbations maybe around it. But you're not allowing yourself the full power of superposition, of entanglement to kind of, show up in that case. So that's the idea, where you want to start background independent with the minimal elements. And then the road is difficult because you're kind of giving up on your notion of, time and space and whatever. And then under what circumstances, which is a question that Prachi you asked, I don't know the correct exact answer, but we are trying, pushing in the dark, trying to see what comes up, and does it match with what we expect or
Right.
what we see, and hopefully eventually make contact with experiments, and then maybe have this path built a little bit more concretely.
So the way you're explaining seems to me that this quantum first approach is rather much simpler than what we've been doing, and the difficulty only comes because we've developed an intuition of this classical world.
Well, that's, I think, a very good way of saying it, And at the risk of infusing more philosophy into this,
Please go ahead.
It's like how, your parents would tell you, don't lie. Like, it's
Yeah.
a simple statement,
Yeah.
right? It's a simple statement. But the complexities of the world make it a lot harder
do
to kind
you?
of project it
Yeah.
into the world you live in.
Absolutely.
So yes, in that sense, the ingredients are a lot simpler, and you're able to kind of start working with them right off the bat. But then the hard part is, how do you translate that simple set of statements of elements into what you perceive as reality around you?
Could you maybe give us an example of how something that we've understood using quantum first approach has been more beneficial than understanding it from the other way around?
Okay, so I can maybe give you a very personal example that I have kind of worked on personally, and it's been a fascination of mine for many years now. So in cosmology, there is this problem of the cosmological constant or vacuum energy. So, and different people have different, opinions about how this can be solved, or whether this is even a problem to begin with, and things exist. But the basic problem, for the viewers is that we have found that there is some non-zero energy in the vacuum of empty space, which is a little odd because empty space is supposed to be empty, but there is still some energy there. And the good thing is quantum mechanics gives it to you for free. If you take a quantum harmonic oscillator, even the ground state, the lowest energy state, has a certain non-zero energy, right? Ground state energy. So we thought maybe this ground state energy is the energy present in the vacuum, and maybe that will explain what happens. But you use standard quantum field theory, and you go and compute how much energy there is in vacuum, you would find a number which is orders and orders of magnitude bigger than what you actually go and observe in the universe.
Right.
And that energy is there because the expansion of galaxies, we have seen it in supernovae data and whatnot. So it does exist. But is our prediction matching with experiments? By far, no. So people try to, do a lot of different things to solve this so-called cosmological constant problem. Now, when I was working on these quantum first ideas, one implication that we kind of discussed was that the particular kind of quantum theory that will have a finite dimensional Hilbert space. So to say that the number of possibilities in a given region is finite. You can't have infinitely many things existing in the region. And this will tie back to black hole thermodynamics. But if you take it that for the moment, just to kind of go along with me for the moment, if you have finite dimensional Hilbert spaces, a consequence of that is that the commutation relation between x and p, Heisenberg commutation, so xp equals I h bar or something, doesn't hold true exactly. You cannot have a representation of the canonical commutation in a finite dimensional Hilbert space.
Correct, yeah.
And the consequence of this is that you have a deformed commutation, which for the quantum harmonic oscillator looks like a suppression of the ground state energy. So it looked like, to me at least, that the natural consequence of this quantum first approach, where you start with the Hilbert space, start with the kind of structures in that Hilbert space, naturally we're trying to point towards a lower vacuum energy, as we've seen in experiments. So have I solved the problem yet? No. But it's an encouraging sign that it kind of gives you this flexibility. It's baked in that formalism right from the start. Maybe that's like one concrete example that I've seen myself at least. Yeah.
And what's the motivation for having a finite dimensional Hilbert space? I mean, as opposed to in quantum field theory, we're thinking about infinite dimensional Hilbert space.
Right. Infinities are great. They really kind of ease out some things once in a while. And finite dimensional things can be easier in some senses and difficult in other senses. But the motivating line of inquiry traces back to Jacob Bekenstein and Stephen Hawking back in the 70s. So they were trying to understand the thermodynamics of black holes. And what they found was that black holes seem to have a certain temperature, and also they have a certain entropy, right? The amount of information contained in the black hole. And that information content, contrary to what you would expect from classical ideas, if you take a box and a box of a certain gas, the number of possible states will scale as the volume of the box. You double the volume, you get double the possible configurations. It's extensivity, right? In the thermodynamic sense. What Hawking and Bekenstein and people found was that the entropy of a black hole is actually scaling as the area of a black hole, which is, first of all, finite, because the area is finite, and it's not volume what you would expect, right? Now, these calculations are semi-classical, so you can put a certain amount of trust in them. And to me, at least, this so-called holographic principle that the amount of stuff that can happen is scaling as the area of a region, not the volume, is a good guiding principle. Correct. Is it exactly true? To be found out, but it's a good thing that we can trust for now, at least I believe, to see what happens. So in that sense, the area of a region is finite. And if you try and add more energy into it, so for example, if I have a harmonic oscillator, one of my favorite quantum mechanical systems, and you want to excite it over and over again. So you do the creation operator, A dagger, A dagger, A dagger. Eventually, you become energetic enough that the energy of that system crosses the Schwarzschild energy of the region it's contained in. And the energy collapses into a black hole.
Right.
The black hole has a finite entropy. If it's like, I can maybe add more energy, do it, but the black hole becomes larger in size. So for a given size, there's an upper bound on what you can do before you make a black hole. And black hole entropies are upper bounded by the area. So that's the motivation as to why we think, at least locally. Globally, I'm no one to say right now what happens. So at least locally, the amount of possibilities that we might have, at least I would conjecture, it's finite dimensional,
Okay.
which is again
interesting.
in departure from quantum field theory, I
Of
guess.
course, yeah.
So I think it's a fruitful line of inquiry to like see what kind of constructive and maybe observable features can we start to see which deviate from quantum field theory, but in the right limit also approach quantum field theory.
Yeah.
So that's what we've been also been looking into a little bit.
Because that's always the theme that, stuff that has been worked so far, any new idea should sort of approach it
Yeah,
in some. No, of course,
yeah,
you're right.
yeah.
Sanity checks are important,
Absolutely.
and quantum field
for
theory
sure.
is great.
Yeah, okay.
So we do want to respect that, the kind
Yeah.
of power it has,
Right.
while at the same time recognizing the shortcomings when you include gravity into it.
Perfect.
And then the question is, how can we play around and how can we modify the structure of quantum field theory per se,
Mm-hmm.
such that it's more amenable to
Mm.
the holographic principle. That's
Mm.
what we've
Mhm.
been trying to approach it as.
Perfect.
Right.
That makes sense.
Now, talking about observables and sanity checks, doesn't it become harder to experimentally verify a quantum first approach in any scenario? Because at the end of the day, to have something truly observed, we need to have a classical idea behind it.
Very true. Very true. And I mean, at least conventionally, that's been the reason why we haven't gotten to a quantum theory of gravity yet, because experiments are not on our side.
Mm-hmm.
They were doing amazing with, the particle colliders, and we got so much to know about the microscopic world. But traditionally, if you want to go down this approach of, colliding particles together and seeing what comes out to understand shorter and shorter length scales, higher energies, I was reading an article where they mentioned that to reach the Planck scale, where you might expect quantum gravitational effects, you would have to have a collider the size of the Milky Way galaxy.
Yeah.
So, of course, experiments are not helping us
Yeah.
to get there right
Right.
now. But now I also feel that there is hope, because quantum information is offering a brand new perspective on these age-old classic problems.
Right.
So when we think about quantum first approach to space-time and gravity, what I'm really trying to do is trying to understand the information content of space and time and how that is distributed, how the entanglement entropy is there, what kind of correlations are being formed, how is space and time emerging from these things. So once we get in the language of quantum information, I think a lot can be done. Has it been done yet? No. But a lot of proposals are coming out, which are tabletop experiments, which can start to explore whether gravity itself is a fundamentally classical or a fundamentally quantum mechanical entity. So you basically let gravity do the mediation between two objects and see whether it lets you create entanglement or not. You got to be careful with what can or cannot create entanglement, but that's the broad idea. Can gravity as a mediating force, can that lead to quantum effects which are not possible classically?
Interesting.
So that's what people are trying to do. And
Right.
I don't do this myself at the moment, but it's definitely something on my mind once we have developed our quantum approach a little bit more robustly, that we want to make approach with experiments more closely as well.
Right. So again, sort of circling back to this quantum classical transition. What's the current update? As do we understand if this transition is sort of is this smooth, or is this very jerky? And this also sort of ties into this whole statistical mechanics emerging from quantum mechanics. Another problem that there's a whole community that is thinking about. You must have heard about the eigenstate thermalization hypotheses, and is thinking about all of this is tied together in this quantum first approach as well.
I would say yes. I think it is all tied up. It is hopefully all tied up in this perspective. Sorry, I missed the first part of your question.
No problem.
Yeah.
I mean, the question is that is this transition sort of smooth,
right,
or
right.
is there a sharp boundary? Is what I was trying to get at. And how do we even approach to answer something like this?
I think we have some handles on this problem of emergent classicality, which itself is a very interesting problem. And I think a lot of my PhD work was involved in trying to understand this problem of how to emerge classicality. We weren't even thinking about gravity at the time. We were just thinking about how do you even emerge non-gravitational stuff from this quantum first approach. And I think the boundary it's smooth, but where exactly is it? It's a little murky. So it's not like something violent happens in the emergence of classicality. Again, that's my perspective. So far, again, we haven't seen any evidence of violations of quantum theory. So I believe that classicality emerges in the right limits by ideas like quantum decoherence, like quantum Darwinism. The fact that records of measurements through interactions are stored in the environment in a robust way. So, for example, if I look at this cup with equations or whatever, and when I interact with this and I see its position, all the photons that have bounced off from this cup are now hitting my eye, and I am getting correlated with those photons to see where the cup is. I am not talking with the cup directly, but rather I am trying to get information from the photons that have scattered and measured this cup and have decohered this cup, for example. So we have some senses as to how classicality and predictability arises from quantum laws. Have we solved the measurement problem? Not really, because again, we have these multiple branches in the wave function. Which outcome we see, I don't know how to predict that. Are we kind of, some kind of a Bayesian understanding? Are we in one of the branches or not? I don't know. But we are making progress in that direction to kind of get there. And the second part of your question about emergence and thermodynamics and ETH and stuff like that, I think there are connections, though I haven't explored them personally with ETH. But again, long-term evolution, where do you thermalize towards? What kind of features do you expect in general dynamics? I think it's questions worth asking. And I think we eventually would like to, talk more with people across the aisle and start to build a better picture of how to put this all together.
Amazing. Yeah. So again, another question along the same lines. Does the quantum first approach inform decoherence in a certain sense, or is it only using like this original way decoherence was sort of proposed and has been
No, it certainly does. And I think in a non-trivial way. That's a good question that you're asking, I think. And it's a question that's not been asked very often. Because again, traditionally, we rely on a classical notion of things, right? You go to the lab and you see an electron, you're like, okay, this is the electron I want to look at. This is the environment, everything else. So you know what you want to study as the so-called system. And then there's everything else, the environment. But then who in the first place told you?
There's no strict demarcation.
Who told you that this is supposed to be your system? You told yourself, right? You told that because this is the object of interest. That's why you have it. So again, quantum theory at its heart, very simple. But only when you divide it up into different elements, that's when it becomes interesting and non-trivial. Quantum entanglement, interactions only arise when you have multiple portions of that same underlying thing. I'm trying to remember this quote by this gentleman, Lanzmann. I may misquote this exactly, so my apologies for that. But the essence of the quote was that quantum mechanics only becomes interesting when we try to divide the universe into parts. And the essence was, a universe without parts is a universe where nothing ever happens. So only when you have subdivisions is where something interesting starts to happen amongst these different parts. So back to the decoherence question, system environment is iconic to decoherence, right? The environment monitors the system and then decoheres the system. But again, how do you begin with a split in Hilbert space, which gives you that? And that was a question that wasn't asked for a very, very long time. Zurek and other friends had asked the question about pointer states, where at the level of the system, what basis of states is preferred, which looks classical. But the bigger question that arises is, how do you split it
exactly.
in the right factorization?
That's what my problem is with Darwinism, like the split, they don't comment about the split.
They don't. And so when I was in my PhD, my advisor, Sean Carroll, and I, we wrote a paper called Quantum Meteorology. And when people see the title, they're like, oh, you misspelled metrology. And let me assure you, we did not misspell metrology. So meteorology is a term.
That would be hilarious.
It's a term in set theory, which I must thank Sean for finding this out, that it's a term in set theory which connects how the parts of a whole connect with the whole, which is precisely what we want to understand here, that how the different divisions of whatever, particles, fields, whatever, connects with the overall Hilbert space. So we called it quantum meteorology. And we tried to give what was I would say, one of the first algorithms, or the first, at least, definitive ways to figure out how would you make the split into system and environment. And we were not even concerned with Darwinism, where you have these multiple records. We only cared about decoherence, system, environment, bipartite splits. And we gave something concrete, which I think is incomplete, but was a first step in that direction. So yes, what you're saying, Bhavya, about is this whole transition, decoherence, is it informed by quantum first? It really, really is, and it should be.
Of course,
And I'm pleased to say at the moment that when we asked this question, about 7-8 years ago, there wasn't much discourse about this. But over the last 7-8 years, many people, respectable people who are working in the field, have started to ask the question as well. And they're also approaching meteorology from this quantum first approach. So I'm quite happy with how things are picking up in this direction.
That's very nice.
And this whole talk about system and environment becomes even more non-trivial when we talk about cosmology, where the structure seeds from quantum fluctuations. But what is the system and what is the environment?
Spoke my mind. Spoke my mind. And I mean, even before cosmology, cosmology is an archetypical way of seeing this out loud. Yeah. But even gravity. When we talk about localization of information, gravity, it's a little weird, because, if I have something here, its gravitational field goes all across space. You can't localize the gravitational field.
Of course not.
I can localize electromagnetic fields, but I can't localize gravitational fields. So what does locality even mean in gravity?
That's
so what does it mean to be here and there and splits and space
and influences?
And
non-trivial questions. And this again, tackles to things like, are we okay giving up causality? Are we okay giving up locality? And this makes me uncomfortable, because, these are pillars that I was taught are foundational to physics.
Correct.
So again, you want to have something which is amenable to finding new structures, at the same time having the right sanity checks that in the right limits, it approaches these beautiful symmetries that we have in the universe. Yeah.
So very true. Yeah. Okay, so let's try to unpack quantum first, furthermore.
Yeah.
What do you mean when you say we treat space-time on an equal footing in Hilbert space, when you talk about the quantum first approach?
Maybe before that, how about you describe space-time from this quantum first approach?
I can only give you bits and pieces, because again, this is a program that's being developed at the moment. And see, time is notorious. Time is very notorious, and the older you get, the more you realize that as well, I guess. But so Einstein, says that space and time are symmetrical in a certain sense, that Lorentz transformations treat them equally on an equal footing. But also at the same time, time is different. Time is not really the same as space, right? Yeah. I can stand still in time, but I can't stand still in... I'm saying this right? I can stand still in space, but I can't stand still in time, right? I'm always moving in time. As long as I have a non-zero rest mass, I'm always moving along my world line, which is, along my rest frame. Yeah. So in that sense, there's some distinctions between space and time. Even thermodynamics, second law, has something very interesting to say over there about the initial conditions of the Big Bang, what happened, what didn't happen. But what I would like to see is that if we really want to treat everything emerging from these quantum first principles, what kind of information structures should exist in Hilbert space, which when you tie them up together, resemble space and time, and then what kind of dynamics separates out time a little differently from space. So can you emerge causal structure right at the level of Hilbert space ideas? So some of my work has tried to understand how time emerges from Hilbert space. And we've done some first few steps in that direction, but we are still not there where we can actually combine everything together and say, okay, this is a space-time emerging from Hilbert space. But we have glimpses of space emerging separately and time emerging separately. And to this, I want to kind of take you back to 2016-ish. So this is during my PhD, and one of my friends and collaborators, Charles Sau, who is now faculty at Virginia Tech. Okay. So he and Sean, they were working on a paper which they called Space from Hilbert Space. So it's a very interesting and a satisfying title. And what they showed was that can you take multiple factors of Hilbert space for a given, let's say, quantum state, and can you sew them up together in a certain way, whereby factors which have higher entanglement are deemed closer in a distant sense.
Okay.
And factors which quantum mechanically have less entanglement are deemed further away in a distant sense.
Oh.
Right. This also ties into the whole ER equals EPR, having like a Einstein-Rosen bridge between.
Correct.
Yeah. Okay.
Correct. Exactly.
Okay.
So how can we basically start from entanglement and then define a
this.
metric?
Oh, okay. Very interesting.
And here space was emerging.
Oh, okay.
So that was an iconic piece of work which has inspired me since.
Wow.
And they've had some follow-ups also on that. So wonderful
Wow.
pieces of work.
Wow.
And then I was looking a little bit towards the end of my PhD into how time can emerge. And the idea was time is not this parameter in Schrödinger's equation. Time is also the clock, a clock is also a quantum system. And the way time flows is the correlations between this quantum clock and everything else in the universe, for example. Now, in gravity, there is this famous Wheeler-DeWitt equation, which is the constraint in GR, where it says that the Hamiltonian of everything, space, time, matter, everything, acting on the quantum state equals 0. So H psi equals 0, which is weird, which means that there's no evolution whatsoever.
Yeah.
So the question and the burden is, how do you emerge and how do you recover time in a otherwise static universe? So time is an internal degree of freedom here. So correlations amongst a clock and everything else in a global static state look like time evolution through entanglement. So we were looking at how that can emerge. So again, distinct approaches, but hopefully one day we'll have more to say about how space and time can be done together.
Right. So this clock, this internal degree of freedom, also treated as quantum. You see how how correlations with the other static part evolves, but
Internally.
Right.
Because if you condition the clock on a given eigenstate or a given time state,
Right.
then what is the corresponding state? And this approach is attributed back to Page and Wouters back in the 80s.
Interesting.
And this kind of was a cute approach that people saw and they admired, but no one really gave much attention to. But now over the last 10 years or so, people have become a lot more open to this approach. The idea is, let's say, even in classical mechanics, if I want to measure the pendulum swing, right, and I want to use the pendulum as a clock, and I want to see what's happening in my lab. Now, the way I keep time is that I look at the pendulum, and different phases correlate with what's happening with my system. So when the pendulum is of a certain phase, my system is doing something. Pendulum is in this phase, system is doing something. So in that sense, time evolution is this conditional correlation of how the pendulum goes and what's happening here. And put together as a movie, it's static, but when you flip through the pages, it looks like, there is this kind of an evolution, which is internal.
Extremely interesting.
That's what at least I think might be a way to look at emergence of time in quantum gravity.
So time basically emerges from from the correlation between this clock and everything else in the universe, which is not how we see time in GR, right? So where does time sit in quantum gravity?
We don't know.
Honestly.
We don't know. There's this famous article by Isham, who in the, I want to say 30s or the 40s, again, don't hang me if I'm incorrect with my dates and stuff, but it's famously called the problem of time in gravity, in quantum gravity. And to be very open about this, people, when they say the word problem, they put a little S in brackets. So the problems of time. It's not one problem. So you're right. And that's the big idea. In GR, time is a coordinate. And there is a whole bunch of invariants that you can choose. You can choose your coordinates. You can choose your time, you can choose your space, and you're good to go. And coordinates don't mean anything in that sense. There's invariance in the coordinates. But then how do you emerge this from a quantum mechanical sense? Is time really a system? So what kind of quantum degrees of freedom can be identified as these clocks? Are they unique? Does it break any symmetry? What about diffeomorphisms? What about Lorentz symmetries? These are all questions that are starting to be asked at the moment. So Yeah, I mean, that's, I think, at the heart of the tension.
Yeah.
And this goes by the name, like in GR, this goes by time reparameterization.
Time reparameterization and variance, exactly.
Yeah,
because
right.
you can reparameterize as
Right.
you like.
Yeah.
But Schrödinger's equation has a certain time parameter inbuilt into it that's just ticking away. So how do you find this right clock in the quantum theory, which has the right correlations, and then hopefully at the level of the full theory, you can restore GR-like symmetry of the coordinates. How do we do that? We don't know yet. But we are trying to ask these questions as we speak. I'm also working on a thing right now where we're trying to understand how can we select in a setting of quantum meteorology, how can we correctly factorize Hilbert space into a clock part and the rest part, which looks like Schrödinger's evolution and possibly even gravity. So those are the kind of questions that we're trying to ask at the moment.
It's surprising and also like so weird that like I think physicists across decades have been aware of these features, but even then these problems were sort of like swept under the rug, and people were like, okay, let's just stick to what we know.
It's
and
part of those rules you don't question.
It's exactly. And again, I'm going to, with great reverence to my advisor, Sean, which I learned a lot, kind of thinking about these questions. And these are hard questions to ask, but important to ask.
Of course.
So Sean, in one of his books, I think it's The Big Picture, the book that he wrote a few years ago. I think in the preface or somewhere initially in the book, he talks about the famous story about the wolf and the grapes. Where the wolf sees these grapes and he tries to get the grapes, and then he can't reach the grapes and says, hey, these grapes are sour, right? So I think something similar that happened in physics as well. That we tried asking these questions from a philosophical standpoint. We wanted to understand the meaning of the multiple branches of the wave function. We wanted to understand the measurement problem. But for one, we couldn't make much progress initially. And second, we didn't have experimental data that could guide us. And thirdly, they weren't important at the moment to guide the next questions that we already had that we could be asking.
Right.
So it was kind of this, perfect storm where we kind of stuck with the canonical rules and didn't question too much because it was risky asking questions about the philosophy of how quantum mechanics is structured. But I think now people are thinking about this differently. We're much more open about the foundations of quantum theory, the foundations of space and time, and we are keen on understanding what really, glues up space and time together. And I think people are hopefully getting more open about the answer could be different than what we have traditionally been used to.
Yeah, otherwise they've been very scared of the P word.
So talking about quantum foundations, for someone who've just started dipping their feet in quantum foundations, the first wall they hit is the measurement problem. So how about you start by explaining what is the measurement problem, and then maybe give some personal insights of how you think about it. What do you have to say about it as someone who's neck deep in quantum first approach and quantum foundations?
Right. So the quantum measurement problem is a problem that if you solve, again, you go to Stockholm for certain. So that should hopefully be motivation enough for young people to at least think about it. But the problem is this, that physics is an empirical science. We make measurements and we understand the universe around us. If I want to go and find out the state of a particle, I go and I probe it, I shine light on it, I do something, I interact with it, and I find out what the state of the system really is. Now, interestingly, in classical mechanics, you can find ways in which maybe you have to be smart about it, but you can find ways where you can probe the system, the state of the system, without disturbing it. So you can actually go and find out objectively what the reality of the system really is and get out that information. Now, quantum mechanics, on the other hand, when you try and make a measurement, you first have to interact with the system.
Right.
And in the interaction itself, you go and you perturb the system in a certain sense. Right. And that interaction leads to you getting entangled with that system, right? So classically, when there's a definitive outcome that, I see the particle here at this velocity or something, there is one unique outcome given the state and given the dynamics.
Right.
Quantum, on the other hand, relies on the principle of superposition. So a quantum system can be in a combination, a quantum combination of many possible classical states. Now, when you try and make a measurement, classically, we only see one outcome when I go and see something, right? But quantum mechanically, if I follow the laws of Schrödinger, when I go and make a measurement, I interact with the system and I get entangled with the system. So I am getting entangled with all possible different outcomes that are possible, which are compatible with Schrödinger's equation and compatible with the initial conditions of the wave function. Now, that was a little maybe too dense at what I said. Let's go back to the Schrödinger's cat, right? It's a archetypical way of thinking about it. So Schrödinger's cat, it's in a superposition of being alive and dead, or if you like cats, asleep and awake, how you want to do it. But once you open the box, in the real world, you'll always see one or the other outcome.
Right.
But in a fully unitary approach, you get entangled with the cat, and there are two different branches of the wave function. One in which the cat is asleep and you are entangled with that asleep state, and the other branch where the cat is, awake and you're entangled with that particular state.
Right.
How do you reconcile the fact that classically you only see one or the other outcome, whereas quantum mechanically, both outcomes exist on different branches of the wave function?
Right.
So that's, at least in a nutshell, the problem from a bird's eye perspective. First of all, how do you explain measurements quantum mechanically using interactions, entanglement, and so on and so forth? And secondly, how do you explain the emergence of predictable single outcomes that you see in experiments? So that, to me at least, is the broad packaging of the measurement problem. Now, I have tried my own things in this field, and it's interesting where we are currently at. I think we are at a stage where we have kind of half solved the problem.
Okay.
We now understand how, at least understand is maybe not as precisely, but we're getting there.
Okay.
We understand how records of measurements of observations get imprinted into the environment, for example.
Yeah.
And the proliferation of robust records is what we call decoherence, Darwinism, and these different branches, when they decohere, they no longer talk to each other. So they are like distinct worlds in a certain sense. So we can kind of describe how definitive outcomes exist on different branches of the wave function, but which branch do I find myself on when I open the box?
Right.
That is still a bit unknown.
Right.
And is there a collapse that happens which is non-unitary and it breaks quantum first approaches? I don't know yet. Or is there something more non-violent where I just happen to find myself on a certain branch? Can I find myself using, Bayesian understanding that this is where I am and this is what I see? But I think those questions are not currently very well answered, I would say. But I do want to say that we've kind of started to flip the problem again by making this idea of measurements not a philosophical question as much anymore, but rather a question of information theory,
Right.
where the information is being propagated, delocalized, where is it stored.
Correct.
Just recently, I was working with some collaborators at the Max Planck Institute of Astrophysics in Germany, and we showed this connection that quantum measurements via Darwinism, where these multiple records are made in the environment, we made a connection of the requirement of good measurements with quantum error correction.
Oh.
So, because again, error correction, you want to, get robustness against errors. You want to get redundancy.
Right.
So, redundancy in quantum error correction, is there a connection with redundancy in the measurement outcomes via classicality? So we try to make a broad connection in that paper. So we try to kind of make this problem not about interpretations, more about the information content that's being transferred. And hopefully, we can come up with experiments at some point where we can start to probe whether one or the other is right or not.
Right. So there's some underlying rules that govern something like this, rather than, hey, to each its own. I mean,
Right.
No, that makes sense.
Yeah.
That makes a lot of sense.
But talking about interpretations, I mean, it's no surprise that you are an Everettian. And so I'm not going to ask you why you support it. Instead, I want to know what are the arguments against Everettian that still does not make it the interpretation of quantum mechanics. I mean, you already mentioned one of those. how we deal with like which branch we end up on. How do we understand that? But what do you think are some arguments that we're still trying to cater to before we call it that is it?
That this is the way
Yeah.
to look at quantum mechanics. So again,
Did Sean even give you an option?
no. Just kidding. This is how you do it. I know the answer.
This is canonical.
Exactly. No, I mean, just to that point, I mean, working with Sean's group, it was a great experience.
Yeah,
It's kind of like, seeing the open-mindedness and the independence of thought,
Absolutely.
and trying to be able to like be okay to ask such bizarre questions, if you will, right? So I
Completely
do
respect
appreciate that a lot.
Yeah.
Absolutely.
And even I am okay to admit that we could be wrong.
Yes.
Yeah,
Maybe
of
I
course.
may feel bad about it, and I may not like you anymore once you have a better theory than mine.
That's what
But,
science is, right?
That's what a science is,
Yeah.
right?
You have to be open to
Exactly.
be-
It should be falsifiable.
Yeah,
Yeah,
exactly.
So I would like to keep our stuff falsifiable, and it's difficult. It's difficult, to be honest, because you got to keep the machine moving as well. So you also kind of have to get more work out, and not all the time you can always have a paper which is exactly amenable to an experiment.
Yeah.
Right.
So
of
sometimes
course.
just having a little bit of ideation here and there is okay, but at least philosophically, deep down, I would want that our work is falsifiable and we keep closer to that. But yeah, as far as we consider about Everett's interpretation, to me, this whole idea is quantum first in the sense that Schrödinger's evolution, Hilbert spaces, vectors in Hilbert space, that's it. That's what Everett means to me per
Right.
se.
Correct.
And to different people, Everett means different things. People can talk about these different branches. How do you find yourself on a branch? What is the reality of outcomes? What is real? And then people have different qualms about what is reality per se. And the famous, Bell's argument about hidden variables,
Right.
local realism, and does many worlds have a role to play in this?
Right.
And recently, again, I've been talking with collaborators about this. And what we kind of seeing is many worlds has not really been used as a paradigm to face questions of, let's say, Bell's
Right.
inequalities
Okay.
and Bell's realism, stuff like that. So I think it's important to start formulating this idea in the language of many worlds. The biggest criticism right now is, again, how do you see single outcome ideas and
Right.
experiments versus these multi-branched wave functions?
Correct.
And is there reversibility in there?
Mhm.
Is there
Yeah.
not? And how do you kind of incorporate second law of thermodynamics? So that's, I think, in my sense, the two biggest things that we should be thinking about.
Right.
Yeah.
But I think these problems are much better than like the collapse argument of like erasing some part of the wave function and just like forgetting about it. I think these
Yeah.
are much more nuanced questions to ask that, hey, how do you end up on a branch and how do we see these things in an experiment, rather than, hey, just delete, some.
Right.
Yeah.
And again, if I'm okay with deleting things as long as nature supports it.
Yeah,
right?
Fair enough.
absolutely, yes,
Right. So
yeah.
if tomorrow, we find some experimental evidence which is telling us that unitarity is not the end game, I'd be okay to maybe switch to a collapse model
Yeah.
or maybe see, where the bridge lies.
Of course.
But so far, we haven't seen
Right.
much
Yeah.
in that sense. And those theories are mathematically very compelling, I must say. So it's
Of course.
amazing to read them and see
Yeah.
how it's happening. But again, I would like to keep an open mind. And again, I'm one part of the
Rightly said.
puzzle, so we'll see how it all fits together eventually.
So my argument usually goes around, so like someone asks me about many worlds, I always say that the many worlds isn't even about many worlds. It's about understanding how the wave function is real. And that's how you move forward. You don't even have to think about, how many worlds there are, which branch you land on. And I feel that is what makes it more complicated rather than what it actually is.
Right. I think if I get your point correctly, it's again this understanding of how do you map that abstract wave function
Yeah.
into
Exactly.
what we
Yeah.
see around us
Yeah,
in the semi-classical sense. And I completely agree with that in that context, that the burden with us lies that we have this simple looking theory where it's just this wave function, just this Hamiltonian, just this evolution. And how do we emerge from there? Structures which resemble space-time and gravity. And once we do it, is the answer to the measurement problem kind of inbuilt somewhere in here? I don't know. But I think this kind of an honest approach to quantum first, I think, is a worthwhile
Yeah, for sure.
thing to look at.
Yeah. So sort of this reductionist way of I won't say summarizing because again it has a lot of nuances, but a reductionist way to understand this quantum first is that you're very much committed to unitarity. Unitarity has to hold, and everything has to be, as you said, quantum, and then you see how things sort of flow out of that.
Correct. So start with this unitary looking evolution with this Hilbert space. And then again, depending on what you want to emerge, what kind of features you want to emerge, what kind of structures can you start finding in the Hilbert space which resemble what you're looking for. That's in a nutshell the kind of bottom-up approach that we're trying to kind of focus on. Right. And I think right now we're in a stage where it's a giant, thing to look at. And we're looking at these different islands of problems. There are questions about emergent classicality, of decoherence, measurement problem, which is its own little island of questions.
Correct.
Which usually has nothing to do with gravity for the most part.
Yeah.
Right? In the last 10 minutes, we haven't mentioned the word gravity per se, right?
Yeah.
And then there are questions about holographic principle. There are questions about area laws of entropy. There are questions about space-time locality. So there are these different questions which are being targeted in the quantum gravity community. And hope is that as we make more and more progress, these different islands will merge together and there'll be a more complete picture which comes out. But many questions to be answered.
So not leaving gravity behind.
All right.
But still a very general question about, there are a lot of candidates, string theory being a very prominent one. So which one of these are sort of in your peripheral vision when you see that this quantum first approach might sort of like marry into one of these approaches the most?
That's a good point. Because again, I say it openly, our work doesn't stand alone, right? It's in a context of other people doing their things. I think the closest approach, at least philosophically, might be more towards loop quantum gravity and causal sets. That's what I would think. Where again, they're not starting with any background independent approach. I think would be philosophically, or at least idealistically, kind of closer to us in this quantum first approach. I think string theory, canonically said, is more background dependent. You start with a certain space-time and then you quantize it or whatnot with strings and everything. But here we are trying to start with space-time not being fundamental. So loop quantum gravity, where there are these different variables which can be quantized, or causals, where you have different points and these different points have a causal order to them, at least are closer in thought to where we are. Right. And hopefully there is a mapping between the two if they are correct, but that's to be seen.
Super interesting.
So before we move forward, something that we've seen traditionally is how things that we consider fundamental at first turn out to be emergent. Do you still think that Hilbert space could be emergent?
Quite possibly so. Just recently, I got this wonderful email from a student, and they asked me a bunch of questions about our work. And I was very impressed to see the students kind of, deeper insights into these problems. And they asked me this exact question. Is the holographic principle, for example, is it emergent or is it fundamental? So again, to me, it's a guiding principle at the moment. It's a semi-classical understanding of what we have. And to me, at least, it may not be the bedrock fundamentals of quantum gravity. What I would hope is that, there is this Hilbert space, there is a dimension of the Hilbert space, there's a certain Hamiltonian, a certain quantum state maybe, and the eigenspectrum, the eigenvalues of these matrices, that defines the theory. And then from there, we kind of make map towards gravity and whatnot. Now, is Hilbert space fundamental or not? Now, if you ask von Neumann, he'll probably say it is.
Of course.
He is really kind of fond of Hilbert spaces. But again, there may not be a reason, maybe in about, a few years down the road, we might find something which says that, okay, this structure is not
required.
Or maybe not the ideal way to think about it.
For sure.
Maybe algebra of observables is something more fundamental. Maybe a structure which is beyond tensor factorizations is a little more fundamental. So I think the degree of fundamentality changes and it evolves, and that's a good thing, I think, as we find out more and more about the universe. What we thought fundamental 10 years is not what is fundamental today. So I'm okay with that. But at least currently, our framing of quantum theory involves Hilbert spaces as the starting point. So I'm okay with using that at the moment. And if tomorrow we find out, okay, there's a different way of looking at it, we'll definitely be open to looking at that as well.
Awesome. So shifting interests a bit, you've been involved in using tools from fundamental physics in civil engineering problems, natural hazard mitigation. Tell us a bit about these other projects and how you got interested in them, and you know what's some of the ongoing work that's happening.
It's a thing which is very close to my heart. This kind of problems that I really want to kind of mention, and so I kind of stumbled upon this accidentally, if I want to say that. So I was talking to a friend of mine who is a civil engineer by training, but enjoys math quite a bit. So he and I were close friends in undergrad days, and he was doing his PhD in civil engineering. I was doing my PhD in theoretical physics. And, you know, as PhDs go, there are these long stretches of time where nothing ever happens and you're just kind of, you know, fiddling with ideas and trying to figure out life and everything, right? So during one of these summer breaks, I was with this friend of mine, and he and I were just chit-chatting about the realities of grad school per se. And as you do, you know, you discuss problems that you're tackling and what's on your mind. And he was mentioning to me that they are approaching the problem of societal risk management, natural hazard mitigation, from a probabilistic sense. That they want to construct a Bayesian approach to understanding what kind of storm surge models or earthquake models, how can that be modeled probabilistically? So you have a very good quantification of the uncertainty that you're looking at. So if you want to make a smart city, if you have a certain parameter for a bridge, you need to know how uncertain those fluctuations might be. So being probabilistic is, you know, being smart, I think, in this case. So he was telling me about the kind of problems that they focus on. And in hindsight, it was trying to understand how to do Bayesian inference. So you start with the prior, you have a likelihood function, you take your data, put in the likelihood, and then you want to sample the distribution that you get, the posterior distribution, right? And to do this, you have to resort to numerical methods, Markov chain Monte Carlo methods, MCMCs and stuff like that, to sample this distribution. And it's a great mechanism to do computationally, but it's expensive when you do it on the computers. So he and I were talking about how to do this. And in that discussion, we kind of found a connection, which I had learned when I was in my undergrad. And I had gone to Max Planck Astrophysics in Germany. And I was working in a group who did radio astronomy. And they were using information theory, classical information theory, to better infer radio signals from the sky for cosmology. So they had developed a bunch of schemes grounded in Shannon entropy, grounded in information theory, and were using this for inference from data. And the question that my friend was asking was eerily similar to what they had been doing back in that context. And here is the genius that the group in Germany had kind of made the bridge. They had said that the probability distribution in the posterior can literally be mapped to the partition function of statistical mechanics. So the probability can go as e to the minus energy for the probability, and the normalization in Bayes' theorem is like the partition function of StatMech. So e to the minus beta e or something divided by z. That z is the Bayesian normalization, and e to the minus energy
is the
posterior, the joint distribution. And you can take the negative log and get a Hamiltonian out of it. And once you have a Hamiltonian, physicists love it when we have Hamiltonians. So we use Hamiltonians right up our alley, exactly. And what we could do was we could use perturbation series. We could use Feynman diagrams per se to perturb around a Gaussian and get the non-Gaussian pieces as perturbations using Feynman diagrams. And this we kind of applied to civil engineering to get faster running models for earthquake models and storm surge modeling. And this worked quite nicely for perturbative distributions away from Gaussianity. And this was a fun little project because
that's awesome.
To be very honest, when I think about these quantum gravity problems, it's a long road ahead, right? It's going to take maybe many years, and it's abstract, it's out there. This was something which was right here, right? And
very tangible.
Maybe have some impact tangibly on something concrete. And that really, touched my heart. I really kind of liked that. So I got more involved, and then he and I, we worked on a bunch of problems. And then the whole stuff so far that we've done is trying to understand Feynman diagrams, perturbative non-Gaussianities in the context of Bayesian inference for natural hazard models.
Wow.
So that's what we've been doing. And the next step that we have right now is to look at trying to go beyond perturbativity and make it much more general. So try to go into non-perturbative methods and see what we can do.
Wow.
So I have basically been this translator, if you can. And I'll admit, the idea's not mine in terms of being novel. I mean, Richard Feynman was the one who came up with Feynman diagrams. People in Max Planck astrophysics were the ones who came up with this bridge between StatMech and Bayes. But I have been this translator between engineering problems and the physics side, and trying to map the physics jargon, the physics language into what can be applied into engineering.
Beautiful.
And that's been very fulfilling.
It makes you
personally.
think how many problems would just be solved if they let physicists run the world.
Right? I mean, only if they all listen to me. The world would be a happier place. But no, I mean, to that point, and just more crosstalk,
Yeah.
I think is important.
Definitely,
Absolutely.
yeah.
And,
Absolutely.
we were talking about this before the podcast also, that there are these different silos that have now kind of come up in science and the world.
Right.
And kind of piercing the barriers through the jargon is really important without judgment.
Yes.
Because often you talk to someone and you're like, it doesn't really
Stay away,
click.
yeah.
This is not
Yeah.
my stuff. This is too good or too bad for me or whatever. And we don't, be honest about it.
Yeah.
And the reason that we were able to break this barrier was because we were friends.
Yeah.
And we could make mistakes in front of each other. And there was no judgment involved. And
Beautiful.
God knows I made my share of mistakes in my calculations and whatnot. So having someone where you can discuss these questions in an open context without feeling the pressure of delivering and just enjoying what you're doing,
Yeah.
which is also a luxury to have. Not everyone has that luxury because,
Right.
work pressures are there.
Yeah.
But having this little side problem that started off as a side problem has now become a very interesting part of my research agenda. And I really kind of want to be pushing on that as
Wonderful.
well. Yeah.
That's wonderful. Honestly, that's very nice. Okay, we're past the hump, moving to the tail end of the whole thing.
Yeah.
On this podcast, we are very curious about, journeys of different researchers that we come across. Everyone has a unique journey. So tell us about yours. How'd you get interested in physics? How'd you end up in your undergrad, then your PhD, and what sort of philosophy do you carry with yourself, and as you navigate through this journey?
Right. So it's a long story.
Go ahead.
Getting old now. So back in my school days, like my high school or even my middle school days, I wasn't much into science. I was a good kid. I got good grades, and that kept me afloat. And I didn't care about science, to be very honest. It didn't call to me, and I was happy, playing cricket and just, living the good life, getting good grades. But around class 9th in my school days, my mother felt that he's getting a little too distracted by playing and not really caring about his life. So she made me join this astronomy club in our school, which was like an NGO-run club that they would do it in the summers. And I was like, fine, I guess I'll go. You had to go, so you went. And the first couple lectures were on, seasons and rotation. And I was like, this is boring stuff. I don't care about the sun rotating or revolving. Like, it doesn't affect me. And like, fine, no one cares. But this group, they took us for a night sky observation. So we went to this little village called Nu outside Delhi, a school trip to observe the night sky. And that was the first time ever where I was literally under the blanket of stars and I saw the shimmering Milky Way for the first time in my life. And that did something to me. It made me see something which I did not know existed. Maybe I had read it, but experiencing it firsthand changes you. And you may not realize in the moment, but gradually you know that was a tipping moment that really happened in your life.
Seed gets planted.
The seed gets planted, exactly. Yeah. And coming back from that trip, gradually my curiosity, I wanted to know more. I wanted to read more, getting more into these books. I wanted to build a telescope. And that kind of just steered me a sharp left into astronomy. Just that one night at this little village, watching the night sky and like seeing what this really is. Wow. And the feeling that I got was this twofold feeling. Part of the feeling was you feel insignificant, right? You see this cosmos in front of you. You see these stars and these galaxies so far away, and the scale of the universe, it's tremendous. And then you see your life. You're like, what is this?
So
Like, what is this parity? Like, how do I understand this? And that kind of, juxtaposition kind of hits you hard. And it hit me hard. Like, who am I in this giant scheme of things? And at the same time, the more I dug into it, I found that physics was a concrete way to understand the universe.
Yes, right.
This connection that I have with the universe.
Right.
I could really, scribble a few equations and I could understand what's happening, let's say, in the Andromeda Galaxy, for example. So that oxymoronic feeling that I feel powerless in the universe, but also I feel some power by doing some things. That's what kind of charted me on this course of physics initially. And then undergrad, I went to IIT Roorkee and I wanted to do physics. I got my choice over there. And I spent 5 years with some of the, the best people I know. One of my friends, I met there, and some good professors. And that's where it got kindled. And across that time, most of my focus was astrophysics in my research. Because, hey, I was a young kid. I asked myself, I like astronomy. What do I do for research? Astrophysics, right? I mean, that's the big reveal. But then the more I did it, I was okay at it. I did a good job, but it didn't satisfy me. And again, it's a great field and people do some wonderful work, but I didn't find my calling per se in what I was doing. So, and then I had a few friends who were notorious about these fundamental questions. And we would go on these long walks while talking about astronomy club work, but talking about quantum entanglement and Bell's inequalities and what is this thing? And that kind of steered me again as a pivot again, trying to shift from hardcore astrophysics into these foundational questions. And I found my way into Caltech for my PhD. And Sean was gracious enough to, kind of have me in his group. And we worked on these problems for about 5 years together, which was great. And I think the one thing I really learned over there with him was to think independently and to not be bound by conventional boundaries that we have, which could be a good and a bad thing, but that's what I learned at least. And then following that, I spent a couple years during COVID as a postdoc with Olivier Doré's group in NASA JPL and Caltech. And that's where my interest again pivoted a little bit into cosmology. So trying to apply this quantum first approach into cosmology.
Wow.
So I spent a couple of years thinking about inflation and early universe impacts of these ideas. And along the way, I was also developing as, someone who loved teaching quite a bit. So I was trying to figure myself out as a researcher, as a teacher, as, who I wanted to be as an academic. And this entire amalgamation of doing my research on these unconventional ideas, but also being able to talk to students and keep the energy alive in the class, I loved that. So I loved teaching more than I can say about it. So I wanted to kind of be in a teaching-centric environment as well. So then life took me to Whitman College in Walla Walla, Washington, this nice, cute little town in the state of Washington. I spent 3 years as a faculty there.
Pacific Northwest,
exactly. And I spent about 3 years there working with undergrads, had time of my life, did some good projects, and got to teach firsthand, which was really great. And I also realized that I also care about learning not just at the level of textbook, bookish equations knowledge, but also how do you experience this learning. So I put a lot of effort trying to make physics a bit more experiential. So what kind of hands-on activities can we do in the classroom to kind of engage young minds, not just to, solve an equation, but to really feel what does it contain, right?
Which is very necessary.
I think so. I really think so.
Absolutely.
So I've been pushing in that direction a little bit lately, trying to reach out and do that. And then we took another big turn in my life and decided to move back to India after being about 10 years in the US. And just happened, not too long ago. And now I'm here at IIT Delhi. Just started as a faculty. So I'm really excited to kind of be here, back to my roots, and kind of give back, but also get inspired by where it all started for me in the IIT system. And again, inspire people, get inspired, and do what feels fun and what feels right, and just let life take its course from here. That's currently where I am at the moment with my quantum first life.
Quantum first lab. I like that. That's beautiful.
You're also very active in the whole science communication. You have a YouTube channel. Even though I see more researchers are now doing outreach, there's still this stigma around science communication. What has your experience been, especially coming from Caltech and like as a student of Sean Carroll, who himself is a big science communicator?
I mean, that was a big influence on me, to be very honest. And again, you don't realize it, but over the years, it kind of leaves a mark on you. And what really impressed me about Sean was the lucidity that, he could talk about these ideas in this very approachable context,
Right.
and be able to connect different looking things and not
Right.
tie yourself down to just, one little, one standard
Absolutely.
approach or whatnot.
Yeah.
So that kind of inspired me. And I've always loved kind of reaching out to people. Teaching was part of it. Even in my IIT Roorkee days, we would go out and we would organize astronomy nights for everyone to come and see through the telescopes. We had a planetarium over there. So I loved kind of talking to people and discussing science and physics per se. So a natural kind of consequence there was that how can I reach more people and how can I do this? So, and one thing I also felt was this divide that we often see between physics being this highly mathematical, highly disciplined science, where it's difficult to, it's a lot of burden to use the mathematics to understand deeper concepts. But I also feel with a high school level of math, you can do a lot just around you.
Right.
So my channel, it's called The Scribbled Equation. The idea was you scribble a few equations, just light back of the envelope stuff, and you can understand a lot of the universe around you.
Correct.
So that was kind of my approach, to keep it simple, but keep it somewhat impactful and little inspirational as well. So that's where currently I am, and I want to do more in that direction as I go forward. So that's, kind of my universe of ideas, that trying to make it experiential, where people can really feel it and keep them open-minded beyond these silos and just be able to talk more freely.
It's the need of the hour, I would say. Yeah.
I think so as well.
Absolutely. But in terms of sort of responsibilities, did you ever get any backlash that, hey, you're wasting a lot of time on YouTube? And
People often think that you're not a serious scientist if you're doing science communication. Did that happen with you?
Undertones, yes.
Okay.
Definitely. And even when I was at Caltech, and I mean, forget science outreach, just think about teaching in a university. When I was teaching at Caltech as a TA, and I would take recitation classes, I would put a lot of effort into preparing for these, and I would enjoy this. I would do experiments in class to show them and whatnot. And the kind of sense I got from my colleagues, and great people, I got along with them very well, but the sense I got was, you are wasting your time. You rather be spending this time on research. Why are you, not focusing on what really matters? And that psychologically impacts you. So I was in a tussle for a long time, like, what am I doing? Is it right? Is it not right? But I kind of went with what I felt was right, and I kept doing it.
Perfect.
And again, I think there might have been many people who may not take me seriously because he spends too much time making YouTube videos maybe, or, spends too much time in the teaching efforts and whatnot. But I feel I can't do one without the other. I have tried that.
Amazing.
But I feel research for me needs teaching as a balance to keep it real and to be able to kind of close the loop from a societal perspective and be able to kind of give back and get the energy back again as well. So that's what I think. And yes, there are people who would, kind of brush it off a little bit. And I hope that they would eventually see that everyone has their own way of doing physics.
Yes.
I respect their way. But so far, I mean, I've also had very supportive, people in my life.
That's nice.
Right from my parents to, my wife, and all the way to my academic mentors, my colleagues. And I also want to say, when I was at Whitman, even those 3 years, being with undergrads and being able to teach them, and even my colleagues there was extremely supportive in what I was doing. So you kind of get this positive feedback. And now that I'm here at IIT Delhi, I feel a similar sense of kind of energy in the faculty here as well. So I'm kind of very hopeful
very good to know.
that things will be good, and I can do good work, and you can connect with good people around. So yeah.
Beautiful. So you mentioned you came back to your roots. So you were born and brought up in Delhi?
I was born and raised in Delhi. I did my schooling here in Delhi, and then at the age of 18, I left home and went 4 hours away to IIT Roorkee and spent 5 years there, and then went across the world to the US for my PhD, my postdoc, my first faculty job. So I spent almost exact 10 years in the US. And then we decided to come back to India.
So how was, talk to us a little bit about how did you sort of navigate this moving back move? Some of the challenges you faced across along the way, and how did you sort of approach this? Because I think this is sort of a recurring theme. A lot of researchers across STEM disciplines work outside for a while, do their training and so on, and try to come back to India. How was the whole experience?
Right. To be very honest, when I first went to the US, I didn't have a well thought out plan. Which was to say, I'll take it as time goes, and whatever is right, we'll do that. But the more I stayed over there, and I got a lot from the US ecosystem in academia, but the more I stayed over there, I kind of realized that something was pulling me back to my roots. And when I say my roots, I mean multiple things here. I first of all mean my academic roots. I feel the amount of energy that there is in India today, the youth, the students, it's changing a whole lot. And a lot can be done in the country at the moment.
Yeah.
And the country I left 10 years ago, it's not the country that I have arrived back today. And I'm extremely glad to see the positive winds of change. And I would like to be a part of that, because I got a lot from this place, right? I went to an IIT, and that institution, that setup, that momentum, it gave me a lot of a push in that direction. And I feel I can connect with these students a lot more. And this is kind of where I belong in that sense. So I find my people here, and I think I can talk with them and communicate and find that connection per se. So I do want to come back and academically kind of give back to what nurtured me to begin with.
Perfect.
And the second part of the equation is my family as well. Right. So that again is part of who I am, and I would want to be in a space where I am close with my family as well. And I feel like being here ticks both boxes extremely well. And I feel I can really kind of do good work in the IIT ecosystem right now, and even beyond, hopefully. And India currently is in a place where we need young people to kind of come back.
For sure.
And come back with enthusiasm. India has a set of problems, no doubt. But again, those problems...
Like every country.
Right? Yeah. Exactly. And I feel that... the decision was big. It wasn't easy to make.
Of course.
And we got a lot of backlash from friends and family, not in a bad way, but in a looking out for you kind of way. Are you sure you want to do this? Very honestly. Yeah. And we thought about it a lot. But again, the thing that I was always come back to is, wherever you are, you always have a bunch of problems. You need to choose which problems you want to face.
Are worth it,
Are worth it for you. And I kind of converged on the fact that these are the problems that I want to face. And I think that the things here in India are changing rapidly. Things may be a little less efficient here and there, but the intentions are good.
Yeah.
So I think we really can do a fantastic job.
Absolutely.
And
to catapult the whole ecosystem into
something great.
Great.
And
absolutely.
Just 3 months I've been here right now, and I've met with students without even teaching a class officially. When I met with students, I have been amazed with the kind of enthusiasm, with the kind of depth that they bring sometimes to discussions, which I don't think I had when I was an undergrad. So just that kind of energy that they have right now, and the awareness and the kind of the wish to do, I think it's fantastic. Right. And also I do want to mention that physics, its status in society has also changed, right? Earlier back in India, you could either be an engineer or you could be a doctor. That was the folklore, right? You either go this way or go that way. And there wasn't much appreciation for fundamental sciences. That is changing today, I think. Right. And maybe because of data science that people have seen that, stats and physics and mathematics plays a key role, but it's coming a little bit more centric in how we think about things. So I think we got to be a little bit more open, accept it, and then ask these fundamental questions, but at the same time be open to, applications and kind of create a nice ecosystem that we can do here. I think India is doing that. The government is supportive of newer projects.
Right.
Younger faculty are coming back. A lot of the older faculty are also supportive of, bringing in new ideas. So I think we are at a good tipping point where we can really start to do good.
That's wonderful to hear.
So you mentioned that you've come back to a different India. Talk to us a little bit about how what like some of the things that you've actually seen that have changed, and maybe comment on like the current status of academia and how it's sort of progressing, as you also just mentioned.
Again, I may get some frowns for this, but when I was an undergrad, the people who would be in a physics degree were people who couldn't get anything else. And I'll be very honest about this, right?
True.
A lot of the people who were there were not there because they cared about the subject, but because they got an IIT rank, for example, and they wanted something in an IIT.
That's rightly said.
And that's what they would be doing. So that enthusiasm in the student cohort was a little low, I felt, at least in my time sometimes. Now when I see these young students in the physics majors across not just IITs, but also other institutes, the tone, the discussions, the enthusiasm has changed.
Wow.
So the kind of, I think, acceptability of core questions of physics, I think it's at a little higher end than what it was when I left. So in that sense, that has been a change. Also, India is becoming a lot more efficient. You know, we would often say when I was growing up that things take too long sometimes to really happen here. They still take time, no doubt. You got to be a little patient here. But the intentions, people are starting to gonna put things together and in the right direction. So in that sense, let's say a simple example like procuring equipment for a research lab.
Right.
It's getting better to do that.
Nice.
It's still difficult. It takes a lot of paperwork to do it. But still, I think the intentions are right. So those things, those little subtle that you really can't quantify.
Yeah.
But the mentality and the kind of approach and the attitude, I think, is becoming more amenable to higher education, I think. Yeah.
That makes sense. Yeah. So these subtle things, as you rightly said, when you actually, when you actually go to these first world countries, right? Sometimes all these subtle things are on autopilot. They're already happening. So when you said that you see something change, that you see that, okay, now these subtle things sort of are taking care of themselves, and there's like more enthusiasm in students, and so yeah, that's you completely rightly said that things are changing for the better, and we're almost at this tipping point where we sort of
right. And I also feel one more thing, that back in the day, the channels of communication were somewhat limited. And by back in the day, I mean not 10 years, but even before that, right? We didn't have things like YouTube. We didn't have things like social media. We didn't have such rapid communication. So fundamental ideas, or just those, they would not proliferate a whole lot. Now, I think because people are curious and there's such a treasure trove that's available out there, that people can really access it a lot more easily.
Right.
So in that sense, information access has also become, a part of this new India.
Definitely.
And just being able to kind of access so much and know so much, and like talk to people that you could previously have never imagined reaching out to maybe.
Exactly.
It can happen now.
Yeah.
So that also, I think, has changed the mentality of the generation, that these things are possible and they are doing it now.
Yeah.
Absolutely.
And lastly, what is one piece of advice you have for young students of science in India?
Right. So that's it's a thing that I think about sometimes. That what should we be doing, same or different, that can help us do better. The one thing I currently feel, especially with the advent of AI and everything, that's something which bothers me a little bit. It's amazing what AI can do, but I also feel that younger students, younger minds are giving up a lot of the thought process in favor of quick output. So you're able to kind of do more, sure, but
sort of this double-edged.
It's a double-edged sword.
Yeah.
So I think, I don't know the answer how to implement this or what is the right approach, but I feel we got to be a little careful about first honing our creative thinking skills and then relying on these tools to be able to get more done, not the other way around, which I think it's a slippery slope where it's easy to go and ask an LLM to do something fancy for you and get something fancy looking as well, at the cost of what you understand and what you are able to develop your mind for. I think struggle is important.
Yes.
To develop certain parts of your brain, to like see how connections really work.
Right.
And I really feel that we as teachers, we as professors, as mentors, the responsibility also lies a bit on us, that how do we inspire people now
Right.
to actually come and talk to each other, to us, to each other, to students, to find the creativity that human connection really offers beyond what tools can solve and do and stuff like that.
Right.
So I feel that the Indian ecosystem where we have a hierarchy, right? In the sense of we respect our elders, we respect our teachers. I think that's a good thing. Not to take it to an extreme level of, that you can't question your elders, you
Yes.
can't question your professors.
Yes.
We want you to question. Respectfully create an environment where questions can be asked, discussions can be had. And then we learn and we can use all these, tools to do more possibly.
Right.
But experience it and think for yourself. I think is the biggest challenge that I see currently happening. The younger generation is more, I can get more done, but at the cost of what we don't know yet. So I really hope that my big advice right now would be, do it the hard way. Make it worth your time right now. And then once you're a little more comfortable, then maybe use these tools, but do it the hard way to start. And it's a little uncomfortable, but it'll be worth it, I think.
Yeah.
And just to make it clear, it's not coming from a point of view that मैंने struggle किया, तुम भी struggle करो.
No, not
correct.
at all.
Exactly. I know.
That's not the mentality at all.
I
Rather,
know.
I would like you to have better things which are good.
Yeah.
So the struggle is not because I struggled and it was hard for me, so this better be hard for you.
Correct.
It's not about
Just making that clear.
Right.
Yeah. No, that's important. I
it's
guess.
important, and absolutely.
Yeah.
I mean, people often make a joke about a law of conservation of pain. Pain is always conserved, or maybe the derivative is positive. I don't know.
Rightly said. Yeah.
But it's more about doing the struggle in a positive sense, which really matters. And again, I think as younger faculty who care about the learning, I am there to help you learn, help you kind of see experiences, be there, and not put you through dogmatic, mindset approaches, but about exploring things in a conscientious way, which really kind of makes sense, but without kind of giving up on the basics. So that's what the struggle is, the struggle to learn. I think that's what really matters to me. I think.
The sweet spot.
The sweet spot, which is really difficult.
Easier said than done.
Much easier said than done. So just like quantum first approaches.
But on that note, Ashmeet, thanks for being on the Nobats podcast. We need more courageous physicists like yourself in the Indian academic infrastructure.
And I appreciate you having me, and you're doing a wonderful job with what you're doing. So I really appreciate that as well. So keep doing this, get ideas out there, have more conversations, and you're inspiring a new generation. So kudos to both of you as well.
Thank you so much.
Thank you.
Thanks.